Dear students, in this class you will be learning potential dividers. In measurement of AC or DC high voltages and impulse voltages, we make use of the instruments which will be having very low range of measurement. Since we cannot apply very high voltage to these low range instruments, we need to attenuate the voltage and then apply a very small voltage to the measuring instrument. Before we actually start with potential dividers, let us know about the basics of potential dividers. Let us consider a simple DC circuit here for understanding purpose, whose voltage is V, and say across this voltage source we have connected two resistors, namely R1 and R2. And current flowing through the circuit is I amperes. By Ohm's law, we calculate current I as V divided by R1 plus R2. Voltage across R1, say it is given by V1, and voltage across R2 is given by V2. Now voltage across R1 that is V1 is equal to current I through resistance R1 and resistance R1 product, that is product of I and R1. But what is I? I is V divided by R1 plus R2. So you can write this as V into R1 divided by R1 plus R2. Similarly, we can write for voltage across R2. Yes, V2 equal to V into R2 divided by R1 plus R2. Now we will look at capacitive potential divider. Here you can see series combination of capacitor C1 and C2, and that series combination connected across source V. Voltage across capacitor C1 is V1 and the voltage across capacitor C2 is equal to V2. We know the relationship between charge on parallel plates of a capacitor, capacitance of a capacitor, and voltage across capacitor Vc, that is Q equal to C into Vc. From this expression we can write for Vc equal to Q by C. So here we understand that voltage across capacitor is inversely proportional to capacitance of a capacitor. Unlike in case of resistive potential divider, here we can write voltage across capacitor C1, that is V1 equal to C2 divided by C1 plus C2 into supply voltage V, and voltage across capacitor C2, that is V2 equal to C1 divided by C1 plus C2 into V. by keeping voltage by keeping the value of capacitor C1 smaller than the capacitance of capacitor C2, we can have voltage V2 lesser than voltage V1. In this way, we can make use of series capacitive circuit shown here as a potential divider. But in measurement of high voltages, maybe AC or DC, we cannot use these potential dividers, that is resistive potential divider or capacitive potential divider, as it is due to some practical problems, and there are some precautions to be taken and some additional elements are to be connected to avoid the problems. So we'll see how these circuits may be used in measurement of high voltages. So first we will take up resistance potential dividers. Resistance potential dividers are the first to appear because of their simplicity, of construction, less space requirement, which means size is smaller, less weight, and easy portability. Let us consider a common form of resistance potential divider used for testing purposes where the wavefront time of the wave is less than 1 microsecond. Here in this arrangement, V1 is high voltage generator terminal voltage. R1 and R2 resistors in resistive potential divider. Where Z is impedance of coaxial cable whose outer conductor is properly grounded. Grounding I will show here. It is used to avoid effect of electric fields. In this arrangement, the measuring instrument is kept away from the potential divider and the high voltage generator. So when the low voltage is to be given to cathode ray oscilloscope, that is measuring instrument placed at a long distance, there will be stray electric field which will have effect on the waveform that is to be measured and observed. So to avoid that effect, this coaxial cable is used. CRO means cathode ray oscilloscope, which you all have used in electrical laboratory. Here in this arrangement, no impedance matching resistors are used, and the CRO offers infinite impedance to the input voltage. Therefore, the high voltage wave that approaches CRO will be reflected with double of the magnitude, and it will be going back towards the potential divider. Since the reflected wave is twice the voltage V2, that is incident voltage, the low voltage arm of potential divider will have to suffer because it is designed for V2, and double of that voltage is going to appear across it. So in order to avoid this problem, impedance matching should be done. For that, resistor R3 is used between the common point of connection of R1 and R2, that is this point here, and the coaxial cable. That I will show in next circuit diagram. Now you can see here circuit B, which is almost the same as that of circuit A, but here R3 is connected as already explained. So circuit B is circuit in A with impedance matching resistor R3. So when R3 is connected here, the reflected wave from the CRO terminals on approaching the potential divider end of the cable will be absorbed by R2 and R3, and hence R2 will not have to suffer, But we can avoid the reflection itself. For that, we have to make use of another impedance matching resistor R4 across CRO terminals. That I will show in next figure. Now in this circuit, two impedance matching resistors R3 and R4 are shown. R4 is connected to the terminals of CRO. The voltage upon reaching the terminals of CRO finds resistor R4 here, which means that, like in case of circuit A and B, the voltage wave won't find infinite impedance. Because of that, the reflection coefficient becomes equal to 0. Hence, no voltage wave will be reflected towards the potential divider. So I'll write in detail now. In circuit A, V2 gets doubled and reflected from the terminals of CRO as CRO offers infinite impedance to it. The reflected wave on reaching the potential divider R2 suffers as it is designed for low voltage. In circuit B also, the voltage wave input to the cable means here coaxial cable gets doubled and reflected from the terminals of CRO, but as it reaches potential divider, it will be absorbed by R2 and R3. Hence, R2 will not have to suffer in circuit C. R4 offers some finite resistance, we can also call it as impedance, to the voltage wave. Therefore, the reflection coefficient becomes 0 since R4 is kept equal to Z. The voltage appearing across CRO input terminals is reduced to half of voltage at coaxial cable input terminals. Which means at generator end R3 is so selected that Z is equal to R3 plus R1 R2 divided by R1 plus R2. Since R1 is much larger than R2, Z becomes equal to R3 plus R1 R2 divided by R3 plus R1 R2 divided by R1. Because R2 is much smaller than R1, so we can neglect R2 in the denominator and get R1 into R2 by R1 here. Now R1 will cancel and Z will become equal to R3 plus R2. For circuit B, V3 dash, that means CRO terminal voltage is equal to V1 into R2 divided by R1 plus R2. As R1 is much larger than R2. For circuit C, V3 dash is equal to V1 into R2 divided by R1 plus R2 into half. Dear students, I will stop here and continue in next class. Thank you.